What do we know about acids and bases so far? Let me move this stuff for you. Oops. The neutralization reaction, right? That's what we learned so far. How do we know we have an acid? Has a hydrogen ion as the cation, right? Okay. How do we know it's a base? Hydroxide is the anion of our ionic compound. Okay. Now that was in general. Now we're going to go a little bit deeper. So according to Arrhenius' definition of an acid and base, that's what it is. Okay. But it's not complete, so we're going to start with the Bronsted-Lowry definition. Lowry, I don't know. Lowry, I don't know. All right. So an acid, and I think I might have told you this before, but is a proton, what? Did I tell you this? Okay, maybe I didn't. Proton donor. What's a donor? Someone who gives something up, right? They donate it. They just, okay, you could have it, right? Oh, sorry.
Oh, I thought they were just like you.
So, what is a proton? Positively charged hydrogen. So it's the nucleus of a hydrogen atom, right? Most hydrogen atoms, there are some that have neutrons, but most of them don't have any neutrons either. So you rip off that electron, and now it's just a proton. That's why we say, okay, an acid is a proton donor, or someone, or a compound, not someone, a compound that can donate a hydrogen ion. Okay, that's what tells us it's an acid. So that kind of fits into what we talked about in acid already. And a base is a proton acceptor. And again, a proton, talking about the hydrogen ion. So really, if we're transferring hydrogen ions, we have an acid and a base. So let's do some examples. I'm going to give you, I'm not going to talk about strong acids and strong bases right now, but you need to have the strong acids memorized. There's like 6 of them, okay? So let me make sure I get them all. So we got, let me use a different color. HClO4. Anybody tell me the name of that, of ClO4? Perchlorate. So this is perchloric acid. So that's one of the polyatomic ions we should know. Anybody got them down yet? Uh-oh. Okay. So we'll just keep writing them on our little 3x5 card. Okay. Yeah, whatever you got to do. All right. So perchlorate, sulfuric acid, nitric acid. Then we have hydrochloric acid, hydrobromic acid, hydroiodic acid. how can we,
Sorry, the super acids we need to bring in?
these are the strong acids.
Strong acid.
Yep. Yeah, we can call them super acid, but yeah, they're strong acids. And we'll talk about why they're strong, but not yet. So you need to memorize these. Or if you want, you can put them on your little 3 bucks, except for Alex. Okay. HI. Hydroiodic acid. And we didn't learn how to name acids, did we, in this class? I don't think we're going to. It's not on the exam, but if anybody wants to know how to name them, I can show you. Okay. So what's example of a base?
Wax.
What'd you say? Wax?
Water.
Water is an example of a base. Water is also an example of what? An acid. Okay, so that's called amphoteric. It is weak, yes. So sodium hydroxide. Does that confuse you? Hope not, right? We know if it has hydroxide, but here's an example of a non-base or a weak base. Why? Can anybody tell me? So is this. So are these. Acids and bases are ionic. Yeah?
Hydrogen bond?
No.
Because it's
Well-
got calcium?
This is
I'm just shouting on it.
no. Okay, so let me just tell you, and this is the reason why these are strong. I just wondering if you can recognize anything. So remember, acids and bases, they're all they're all aqueous solutions, right? If you have sodium hydroxide as a solid, it's not a base. It's a salt. Okay? You don't want to eat it because if you put it in your mouth, now there's water in it, right? Now it dissolves and now it's a base. So they're all aqueous solutions. And do we know what makes a compound aqueous? If it's soluble in water. We know this? Okay, so if it's soluble in water, it's aqueous, therefore it could be an acid or a base. Okay. Do we see anything else? For example, those components are soluble ions. You with me? Notice HF isn't up there because fluorine's not a soluble ion. Okay. What about this? Is this a good example of a base? Is ammonium soluble?
Yes.
Always, right? Yeah, so that is a good base. Why is that not a good base?
It's not soluble in water.
It's insoluble or slightly soluble. It might be slightly, but yeah. So that's how we tell if it's a strong acid or a strong base. If it's completely soluble in water. But we will get to that in a minute or later. Okay, another example of a base, so I'm gonna get rid of that one, is NH3. Anybody know what that is? Ammonia. Okay, that's the stuff that has a strong smell to it. Okay, ammonia. It doesn't look like it should be a base, right? Because hold on, Can this thing attract a hydrogen ion? To make ammonium, and that's why. That's why it's a base. Okay? It doesn't look like it because what should attract a proton or a hydrogen ion? Sure, hydroxide. Why does hydroxide attract to it? Because it's negatively charged. What about this? Is that a base? Yes. What about this? Yeah, those are all bases. Anything that can attract a hydrogen ion would be considered a base. Now, again, we have strong bases and weak bases. What determines if it's a strong base? If it's completely dissociates in water. It's completely soluble. Okay? So strong acids or strong bases, basically a soluble ion metal with hydroxide or ammonium with hydroxide. Those are going to be our strong bases, and that's it. We already kind of learned about that. Hydroxides are bases, right? But we also learned just barely that not all of them are. Okay? Any questions how to tell what compounds are acids and what compounds are bases? Okay? So I'm going to throw a couple more out there. So we got water is a base, but water is an acid. It's not a strong acid. I'll just put it right there. Okay? And when we have compounds that can be both acid and a base, we call it amphoteric. And if they could both be an acid and a base, you think it's a strong acid or a strong base? No, it's a weak acid and weak base. But we'll get into strong acids, weak bases, strong bases later. Okay? So again, I'm going to put down in here, maybe I put down in the definition, aqueous solution. Sorry, I should have wrote this before. So it must be an aqueous solution in both cases. So an acid and a base, they're both aqueous solutions. So let's just do a simple example of an acid. We got HCl breaks down into H plus and Cl minus. This is the acid component. What's that? Oh my gosh, that's crazy, right? So an acid will turn into a base once it gets rid of its hydrogen ion. And the base will turn into an acid once it accepts its hydrogen ion. Does that make sense in your mind? Okay.
So just to be clear, we're talking about still if there was show up on like a pH test,
What's that?
like if I tested these
Uh-huh.
acids and bases on a litmus strip
Uh-huh.
or whatever. Okay.
We will talk about pH a little bit later. But you can have, your strong acids are going to be on closer to the 0 end, right? And your strong bases are going to be close to the 14 end. But we'll get there. So an example of a base, and of course this is a strong acid, completely dissociates, and we get all this and all this, right? Don't get any of that left over. And then, let's see, A strong base we talked about is sodium hydroxide. Breaks down into sodium and hydroxide ions. And this is the part that tells us it's a base. Good?
Because the H is negative.
OH is negative. That's hydroxide. And it is an anion, and that's what accepts the proton. And turns into what? Water. Which is an acid. It's a weak acid, but yeah, go ahead.
Would the sodium be considered the base? Or sorry, the acid?
Nope.
Why not?
Because it doesn't have a hydrogen ion
Oh,
to give away, right?
So the one that has hydrogen ion is acid.
Yes. Uh-huh.
but,
Okay.
but up above, you were saying how like sulfate, for example, is a base because it's a proton acceptor,
Uh-huh.
even though it doesn't have hydroxide.
Yep.
So how is-
Because it's SO4 minus. Since it's a negatively charged particle, it's going to attract what to it? Positively charged particles. This is not going to be attracted to that, to the hydrogen ion. It's not. It's not going to say, hey, give it to me. I'm the acceptor of hydrogen ions. No, it's not. Does that make sense?
Oh,
Because it's positively charged.
right. But if it's a proton donor to hydroxide, couldn't it be considered a
The acid tells us it has an extra hydrogen ion attached to it. This does not. This is not a hydrogen ion. This is a hydroxide ion. Good? Let me know. All right. Let's do one more. So if we have H plus, so like if we threw HCl in water, it turns to H plus and Cl minus, both aqueous, right? So H plus with water turns into hydronium ion. So H plus and H3O plus can be used interchangeably. Because H plus, if it's in water, it's going to be H3O plus. You with me? But it's a lot easier just to write H plus. But if you see it as H3O plus, it means the same thing. Are we good? And it's all balanced, so it's a 1-to-1 ratio of H plus to H3O plus. Good? So let's talk about the two exceptions. We have water. If I draw the structure of water, it looks something like this. And if I draw ammonium, it looks something like this. Right? And this hydrogen ion could then hook onto the oxygen and says, hey, I don't have any electrons. You have 2 electrons. It wouldn't hurt you, and it would just help me, right? To have that octet. And so it can hook up there to create H3O plus. And if we do it for ammonia, we got H plus. It's saying, hey, same thing. And it turns into NH4 plus. That's how it's able to do that. Good? Any questions so far on how you tell if it's an acid and a base? So let's look at some examples of amphoteric.
Sorry, just to clarify, H3O plus is a,
Yes. Now, why is that?
It has an extra.
It has an extra H plus that it can donate.
so it's an acid, you
It's an acid. So is NH4 plus, also an acid. Because if it gets rid of that H plus, now it's just ammonia. Yeah. And once it donates, it'll turn into a base. Okay? So amphoteric again means it could be an acid or a base. So the examples are H2O. We could have HSO4 minus, right? It's an acid because it has an extra H plus. Has an H plus there that it could donate. And it's a base because it doesn't have an OH in there. Remember, OH is the Arrhenius definition of a base. But here we have a negative charge that could accept a hydrogen ion, a plus charge, right? That's what tells us it's a base, yeah.
But once it's sulfuric acid, H2SO4, then it would just be,
An acid, yep, because it's no longer charged. Yep. So we could have HCl3 minus, H2PO4 minus. Good. All of these are amphoteric. Are we good? Should we practice this before I move on? Okay, this worksheet that you picked up, section 1. Determine if the following are acids, base, or amphoteric. Or neither, I guess.
ammonia would be a base,
Ammonia? Yes.
because it accepts one.
Yeah, well, can ammonia give up a hydrogen ion? No, then it becomes something that's inexistent, right? So it can't do that. So just because it has a hydrogen in it doesn't mean it's an acid, right? Has to be a hydrogen ion available, so it has to be a what? Ionic compound. NH3 is a covalent compound. So is water, but, okay. Does anybody want to go over, what about CN minus? Acid, base, or both? Base, because it's an anion, right? Okay. Any other questions on section 1?
What about hydrogen phosphate?
Hydrogen phosphate.
Is that amphoteric? Well,
HPO4 2 minus? Yeah, what do you think? Is that amphoteric?
no, H2PO4 is.
These were just 1, 2, 3, 4 examples that I gave you.
So,
Is this one?
no,
Is that amphoteric?
No,
No? Why not?
because it's a 2 minus and now a minus minus.
Does a 2 minus attract a positive? More or less? Even more.
so it's a base.
It's a base.
But it's not an acid at all.
Does it have an extra hydrogen ion sitting there? Yes. This is amphoteric. Just like this one. Just like this one. Just like this one.
Because it could give that hydrogen away.
If it has a hydrogen ion to give away, it's an acid.
Yeah.
If it doesn't, and it has a negative charge, it's only a base. If it doesn't have a negative charge, it's neither. So what about NH4 plus? Acid, because it has an extra hydrogen that it could give away. So that one's one of the exceptions, right? So don't just look at the charge to determine if it's an acid or a base. Got to look at everything. And that's why if we know the structure of it, we can kind of make sense of it a little bit more. Andrew.
Sorry to wrap my head around NH3 and NH4.
Okay. NH3 by itself does not look like a base, does it? It does not. It's one of those exceptions. And it's a common exception, so we need to know it. NH3 ammonia is a base. Good?
Just because it is.
Because it can accept a hydrogen ion. And when it does accept a hydrogen ion, did I write that up? Yeah. When it does accept a hydrogen ion, it becomes something that exists, ammonium ion. Are we good?
What about, calcium 2 hydroxide?
What about
Or is calcium?
CaOH2? Yeah, that's a base because it has a hydroxide ion. Does it dissociate? We can't tell, right? So maybe, according to our list, we would say neither acid nor base. Because I think calcium is one of those that does, and I didn't give you that exception,
So that'd be kinda like the iron one you gave earlier, right?
but iron's not one of the exceptions. So calcium, strontium, and again, I didn't put these on your list, so you don't have to worry about that in this class, okay? But, yeah, go ahead.
Sorry, Vicky said that one's a base.
Yeah, it is.
How is it both?
It's
Or
not
neither?
both.
Sorry, how is it neither and a base?
It's not. It's just a base. But for this class, for what I gave you for the solubility chart, if you put neither, I would be okay. What does that mean? I will not test you on that. Good? Only test you on the exceptions that I cover in class. Okay? Any other questions on section 1? Okay? So now let's take a look at acid-base reactions, unless we have any questions up to this point. So we learned about one type of acid-base reaction already. It's called a neutralization reaction. And that's when we have a strong acid reacting with a strong base. Remember I told you if you get this strong acid in your eyes, you're going to go blind. If you get this strong base in your eyes, you're going to go blind. But if you put them together in the right proportions, you can drink it. It's just salt water, right? Don't. Because how many times are we perfect in a lab setting? 0 times, right? Well, 0 times for you, but what about, okay. So our neutralization reaction is definitely an acid-base reaction. And these are the easiest ones to predict. We got HCl in aqueous form plus NaOH in aqueous form. Breaks down and gives me what? Water and salt. Water as a liquid. And NaCl, it's still in water, so it's aqueous. Good? NaOH, NaCl. Okay. and this is H2O. Okay? So we can see here's our acid, and what does it turn into? A base. Is this a base? Very, very, very weak base, if we want to call it a base, because it has that Cl minus that can accept a hydrogen ion. Does that make sense? And this right here, this hydroxide, that's our base. It turns into a what? A weak acid. An acid turns into a base turns into an acid. So if you have that, you're going to have an acid-base reaction. Now this one's pretty straightforward. If you get salt and water, have an acid and base, get salt and water, it's a neutralization reaction, and it is an acid-base reaction. Any questions on that one? That one's just review. But if you have a question, let me know. Okay, the next one, let's go a little bit more complex. H2SO4. Is that a strong acid? It is. So that's one of those that you have to memorize. If you can memorize all the strong acids, then all the other acids are what? Weak. So it's going to be to your benefit that you memorize those. So that's an aqueous form as well. Plus H2O. Is this an acid-base reaction? Because this could be what? Either an acid or a base. This is definitely the acid because it's definitely not a base, right? And so we're going to get, this guy's going to donate a hydrogen ion and become HSO4 minus, for example. And if this guy accepts a hydrogen ion, what does it become? H3O plus. Are you with me? Or we can essentially say H plus aqueous, right? We could, because aqueous tells us the water is there. So here's our acid. Here's our base. And our acid turns into a base. So this donates a hydrogen ion. Therefore, it started with 2, now it has 1. It donated 1. You following? It's not donating it to HSO4 minus. It's becoming SO4 minus. Who is it donating it to? The water. Or the base. You with me? And so we call HSO4 a conjugate base. Acid turns into what we call a conjugate base. Okay? And what does a base turn into? What kind of acid? Conjugate acid.
So it's like a conjugal visit of the hydrogen?
A what?
Conjugal visit of the hydrogen?
Yeah. Okay. Are we good? Yeah.
Just like performing that reaction, how did you get HSO4 minus and H3O plus?
Because this guy donated a hydrogen ion. It just donated one of them.
So it just loses one.
It loses one of the hydrogens and a plus charge, and that's why it's now negatively charged. Good? And it donated it to the water, so now the water is H3O plus, or ammonium, or hydronium, sorry. Good? So this accepts a hydrogen ion, telling us it's the base. Are we good with this so far?
Why is it called conjugate base? and
Conju-
conjugate?
Conjugate?
Yeah, kind of.
Let's look up that word, conjugate.
Context, I know that word, it does not apply.
Conjugate. Combine,
Like, we just let those hang out, would they go back to their?
it means uniting or forming a compound, I guess. I don't know.
That doesn't help.
No, it doesn't. Okay. So this is the conjugate to this acid. Well, why do we call it conjugate base? Because now it is a base. In this over here, it's the base, not the acid. Now I know this could be both, but this one can't be both. So an acid always turns into a conjugate base, and the base always turns into conjugate acid. Good? Should we do another one? Do you guys want to do it on your own, or should I help you again? Help you one more time? Then you're on your own? Okay. So let's do HSO4 minus plus, that's okay. H2O, so this is aqueous. This is a liquid. Can anybody tell me what I get? What does HSO4 minus turn into?
Sulfate.
Sulfate, SO4 2 minus. And what else do we get? H3O plus, hydronium ion. Okay, so tell me the acid in this reaction. HSO4 minus, that's the acid. Where's the base? The water. The acid and the base are always on the reactant side. Okay. And what's SO4 2 minus called? Conjugate base. And the H3O plus is then called conjugate acid. So this donates, it loses one, and this gains a hydrogen ion. Yeah, Andrew.
Are these still neutralization reactions?
These are not.
Okay, so
No.
is there a word for these, are these conjugate?
This is just an acid-base reaction. There's a lot of different acid-base reactions. They all concern with an acid and a base. And they all turn into a conjugate acid and a conjugate base. All of them, even neutralization reactions.
So if I took tomato juice and bleach, I would end up with something like this?
Yeah.
Okay.
But tomato juice, we can extract the acid out of it, right? And bleach, we can, well, it is the base, but, okay. What?
That's
Donor, it donates. Slow down. We're not in a rush. When I first taught this course, it was in summer, and we had all of the exams in class, and we had to push to get stuff done. And that was the first time I taught this course, and so I'm always in a hurry for some reason. I need to changed I'm not making excuses, I'm just saying, I need to work on it, right? All right. Any questions so far? Okay, let's look at section 2. Do we need one more that doesn't have water in it
Yeah.
before we have you try one on your own? Okay, let's try this very first one. So we got Na2CO3 in aqueous solution plus HCl in aqueous solution gives us NaHCO3 in aqueous solution plus NaCl in aqueous solution. So this doesn't look like our standard acid-base reaction because it doesn't produce a liquid, right? But it still is. And, well, we can prove that, right? So where's my acid on the left side? Remember, the acid and base has to be on the reactant side. So where's my acid? HCl. That's the only one with a hydrogen ion, period, right? So that's my acid. Therefore, this has to be my base, is it? What part of it is my base? Yeah, this dissociates into Na plus and CO3 2 minus. If we write the ionic equation, right? That right there will attract or accept that hydrogen ion. So that is my base. Okay, so where's my conjugate base?
The NAC, or the other one.
Why?
Okay, so wait, why, yeah, why would that?
Why? Because an acid will turn into a base after it donates its hydrogen ion. So why does it hook up with Na? Because that's the other guy. It's a double replacement reaction. This is still an aqueous solution, so this is still a Cl minus, right? That's the only base in that situation. It lost a hydrogen ion, so now it's a base. It could accept a hydrogen ion, right? And making this, does that have an extra hydrogen ion it can donate? Yes, right there. So this is my conjugate acid.
So a conjugate acid would still always have a hydrogen?
Yes.
Okay,
Otherwise, it's not an acid.
okay, so there, okay.
So these first two I did were simple ones. Should we make this one a simple one? We have CO3 2 minus plus H2, well, that's not a good one. If we have HCl plus H2O. And no, that's not a good one either. Yeah, I'll do it this way. CO3 2 minus. It doesn't make, it's not the same one, but it's kind of a simple one like it. So this is H2O. This goes to HCl3 minus and H3O plus. So if you had a hard time seeing that that was an acid, right? This is a base, it turns into an acid, conjugate acid. This is an acid, turns into, uh-oh, that's wrong. Because this is not a conjugate base, is it? So, yeah, that wouldn't happen. That's what happens when I try pulling stuff out of my head. So just erase what you wrote. Ooh, but I have a pen. Sorry. Okay. Do you guys want to try one now? Try number 2 and or number 3 or both on section 2 in your on your worksheet.
Number 2.
Should we do number 2?
Yeah.
NH3, we cannot say the base.
NH3 is what? A base. You need to just know that one. NH3
But
ammonia
NH4 has a conjugate base.
is a conjugate acid
Acid.
because the base accepted a proton and now it's an acid, right? Does that make sense?
The H3PO is just acid. Because it has the
H3PO4, that's an acid because
of oxygen and
has
hydrogen.
not because the oxygen, because it has a H plus as the cation. H is out in front. Now H doesn't always have to be written out in front. Should I show you an example or are we still working?
I just wanna go over number 2.
Okay, yeah, let's go over number 2. Okay, we got H3PO4 plus NH3, they're all aqueous, goes to H2PO4 minus and NH4 plus. So here, out of these two, this one cannot be a base. Right, so that was the acid. This one cannot be an acid, so that has to be a base. Well, hold on, it has hydrogen, it has hydrogens in there, but what doesn't it have?
An extra
Hydrogen ion. This is a covalent compound. This is just that one exception you need to just have down. Okay? So what does H3PO4 turn into once it donates? Turns into that. Therefore, this is the what? Conjugate base. I know it's also an acid. This is amphoteric, but it's coming from an acid turning into a base.
I see, okay.
Good? And the NH3 becomes NH4, so this is the conjugate acid. Now it has an extra H plus hooked onto there. Yeah.
So, H2PO4 minus is a amphoteric, it's an acid, but in this reaction, it's a conjugate base.
Yeah. Yep. The amphoteric means it could be either or. In this case, it's the or, right? Sorry. Good? Anything else? The third one? Yes, we can. We got HBr plus NaOH What does this look like? Strong acid, strong base, breaks down into, does a double replacement reaction, is water and salt. Not the kind of salt that we eat, but it's a salt. Yeah.
But how is sodium bromide acid?
It's not. It's a base. This acid, remember, this guy donated a hydrogen, this whole thing donated a hydrogen ion. What's left when it donates? The Br minus. Well, is that Na really there, guys? No, it's dissociated. How do we know it's dissociated? Because it's aqueous. We good? So this is the acid. This is the conjugate base. The acid turns into the conjugate base. And the base turns into conjugate acid.
So we don't look at like the distribution of the hydrogens?
What?
We don't look at like the distribution of the hydrogens?
Yes, we do. Because if this guy accepts a hydrogen ion, it becomes H plus OH minus, right?
Yeah.
Which is just water.
But the one that accepts the extra hydrogen isn't always going to be the conjugate acid, right? No, it is. That's what I figured. Okay. Yeah.
Yes.
Yeah.
Yep. How we feeling? Like we need to do 39 more? Do 40 just in case. No, sorry. You want to do one more, or how we doing? How we feeling? Okay, here we go. So let's do K2CO3 in aqueous form plus HI in aqueous form. Is that okay that I don't write that? I have a hard time writing that very good. H2CO3 in aqueous form plus Ki in aqueous form. Okay. Which is easiest to recognize, the acid or the base? Acid. So which one's the acid? HI, right? Therefore, this one must be the base. Can we make sense that it is a base?
Yeah, because
CO3, it's an aqueous solution, so it dissociates, and that CO3 2 minus picks up the H plus. So that's our base. And the acid turns into what? Which one of these? First or second one? Does that make sense?
No.
If this donated a hydrogen ion, what is it? It's HI.
Yeah.
Sorry. It's I minus.
Yeah.
You with me?
Yeah.
So the HI donates a hydrogen ion, because it's an acid, and now it's the I minus. But now there's an extra potassium in there. Does it really hook up to it? No, it doesn't. We just put it there because it has nowhere else to be, right? Okay.
So then
So-
that's the conjugate base.
Conjugate base. The acid turns into a conjugate base, and the base turns into a conjugate acid. So this time, how many did it gain? 2, right? And why did it? So that it could be neutral. But would it really hook up, guys? No. They don't really hook up.
So you
Why?
just have like this weird acid-base solution floating around
Yep.
in. Gross.
Yeah, so did it neutralize it? No. Neutralization reaction forms a conjugate acid and conjugate base, but they're neutral. Turns into water, which is neutral, and salt, which is neutral. In water anyway, right? Okay. Questions? All right. Now that we got the foundation of acids and bases, now what? We can do stoichiometry. Oh, are you guys excited? Ah, love stoichiometry because is it still what do we call that? A mill around your neck? Millstone around your neck? Is it? Millstone around your neck? Okay. It's just what? Dimensional analysis using the mole roadmap. And you have that mole roadmap, and we're gonna use the rest of that mole roadmap, but just remember, we can't use that, it won't be on the exam. Okay? So if you like that new that mole roadmap that I gave you with the extra acid-base part, then you better write it on your reference sheet, reference card. Okay? All right, let's do we need a review for stoichiometry, what stoichiometry is? I'm seeing no's. Do I see any yeses? We will do stoichiometry, just not a basic stoichiometry. Okay? So let's, because when we deal with acids and bases, what do we deal with a lot? Concentrations, right? So we're going to use molarity as a conversion factor, right? So let's do this. So here's our first example. We have HCl plus calcium hydroxide, and that forms H2O as a liquid, and calcium chloride. I better write this. AQ, AQ, and AQ. What's the first thing we got to do?
Is it CA?
Balance it. Ca parenthesis OH parenthesis 2. So we got to balance this. There's 2 chlorines right here, so I better put a 2 right there. 2 hydrogens, so we got to put it right there because that has 2 hydroxides, 2 hydroxides. You guys see how I did that? I kind of just thought this is HOH, right? There's only 1 hydrogen right here. That's why I put a 2 in front of it. Now there's 2 hydroxides, 2 hydroxides. You don't have to do it that way, but if you can see that, it might make it a little bit quicker. But are we for speed? No, we're for accuracy, right? So let's, if that doesn't make sense in your mind, if you do it a different way, that's fine. That's a 2, not a Z. All right. So now it says, how many moles of HCl will react with 350 milliliters of a 0.200 molar concentration of calcium hydroxide. All right, so this is just a word problem. What's our first step? What do we know? Sure, we can start there. What do we know? Looks like we know the acid or the base.
The base.
We know everything about the base, nothing about the acid. So we're going to start with the base. What if we know everything about the base and just one thing of the acid? And we still start with the base, right? Start with whatever substance that you know the most about. Does that make sense in our minds? Why we start there? Okay. All right. So we know we have 350 milliliters, that's a volume, and we know we have a concentration of calcium hydroxide. What can we do with that? In fact, before we do with that, what are we looking for? We're looking for moles of HCl. That's our question. Okay? Okay, what can we do with what we're given? Well, let's see. I say, here's my dilemma. I just don't ever know where to start. You ever feel that way? Okay, so let me pull this up here. And show you how to read it. Okay, what are we looking for? Let's circle in red. What are we looking for? Moles of our acid. Do you see how there's an A right there for acid? Oh, that's nice. And what's the B for? Oh, isn't that beautiful? Ah, I love that. Okay. So we're looking for moles of acid because HCl is an acid. And, well, what do we know? We know the concentration of our base. There it is. This is what we know. And we also know volume of our base. And we want to go this way, then this way. 2 steps, that's all it is. You understand how to read this mole road map? We'll get into this part later. For this problem, we're not going to use the right side of this. Are we good? Okay, so we're going to start with our molarity, or our volume, doesn't matter. But it's 0.200 molar concentration of calcium hydroxide. And what does it say to do? It says to multiply by the volume. Why do we multiply by the volume? This is moles over 1 liter of solution, right? So when we use that, when we use dimensional analysis, don't ever use molarity. Always change that to moles over liters we talked about, right? Now, can we cancel this and this yet? We got to do what? Convert milliliters into liters. 1,000 milliliters to 1 liter. Now what cancels? All the volume. Woo! I know that's not on the mole roadmap, but can you guys do that so far? Why now? Okay. So now we have moles of our base. If we wanted to calculate that, we could have that, right? We're not here yet, so we keep going. Multiply by what? Yeah, our mole-to-mole ratio. What's the mole-to-mole ratio here?
1 to 2.
Yeah, 1 to 2. So we have this on top, it better be on bottom, right? 1 mole of calcium hydroxide to 2 moles of HCl. And we're looking for moles of HCl. Everything else cancels out. We're done. With our dimensional analysis, now we got to multiply and divide. Was that helpful?
Yeah.
Do you understand how to use that?
200.
0.200.
No, this. 200.
2 moles. Yeah,
You can always start with the 350 milliliters.
you could.
And then put the 200.
Yes.
moles
Do you still multiply them? Does it matter if you go A times B or B times A? It doesn't. So yes, we could have started with volume, definitely. I just showed you this way because this is the way the mole roadmap tells us. But yeah, no problem. And we do this, and we're going to get 0.14 moles. And just to, when I did my notes, that's how I did it, Mariana. That's exactly how I did it. So it works. Get the same thing. Moles of HCl. Don't forget to include what substance we're talking about. Good? How are we feeling? Was that anything new? Well, I gave you the mole roadmap of how we do that. But I think we've done one of these before, right? Maybe? Maybe not. Okay. No? So it's all new. But it's just dimensional analysis, right? When I say just, I'm not saying it's easy. I'm just saying we need to get it down. Okay? You want to do another example? Maybe a little harder example? All right, here we go. So we're going to use this same equation. So I'm going to have it balanced already. 2HCl plus CaOH2 gives us H2O plus calcium chloride. Put a 2 right there. Okay, it's balanced. And this time it says, how many liters of a 0.125 molar concentration of HCl would react with our same 350 milliliters of our 0.200 molar concentration of calcium hydroxide. Yeah, we want to know how many liters of this concentration of acid do we need? Because if we dump too much of it in, it's not going to neutralize, right? If we don't dump enough, it's not going to neutralize. We want to know how much do we dump so that it neutralizes. And when it says that, we know we have a neutralization reaction, right? Another word we call that is it titrates. Okay? You guys do the titration lab yet? Okay, you'll probably do it coming up here. And maybe I'll show you an example of what you're going to be doing in a titration lab, yeah? Would that help? I think you guys do titration labs. Is that, anybody look at the schedule? Are you doing that? Okay. It's just a way to determine what the concentration is. So if I knew the volume, I could figure out the concentration, right? All right. So let's start with, what are we looking for? We're looking for liters of HCl solution, right? That's our question. And we know our concentration of HCl. We know volume and concentration of our base. So where are we going to start? Acid or base? Why acid? Why base?
We're looking for acids, which is
Yeah. We know everything about our base. So we're going to start there. Don't start with what we're looking for, right? Make sense? Okay. So we can do this the same way. Let's do it the way Mariana said last time. Let's start with 350 milliliters first. And we know we got to convert that to what? Liters. So 1,000 milliliters to 1 liter. That goes away. And now we can multiply this. Do you want me to pull up the roadmap again?
Yeah.
Because we're really doing the same thing, aren't we? We're just not stopping here this time. We're going to here. We want to, no, we're not. We are going to volume. Somewhere in the middle, right? Okay. But we use molarity as our conversion factor. Good? So this time, we're starting here again, and we're going here. Just one more step. Good? So we're basically copying this part. So now we're going to multiply by 0.200 moles of calcium hydroxide. Y'all with me? To 1 liter solution. And there my liters goes away. Okay, after we're done with this, we can take a break, unless we have questions. Now we have moles of our base. So now we're right here. Now we use the mole to mole ratio to get to moles of our acid. And it's still the same ratio. 1 mole of calcium hydroxide to 2 moles of HCl. Moles of our base go away. We have moles of acid. Do we want moles of acid in our answer? No, so that means we've got to get rid of moles. How are we going to do that?
1.25 moles on bottom.
Oh, 0.125 moles of HCl per 1 liter of solution. And we want to know how many liters, not milliliters, so we don't have to convert it again. But if it said milliliters, we just convert liters to milliliters again. So moles of HCl go away, so we have a solution of HCl when we're done. And when we do this, we get 1.12 liters of my HCl solution. How are we feeling with this? Anybody feel like, oh my gosh, this is going to be the hardest exam ever? Yeah?
Not yet.
Okay. So where's our struggle? With dimensional analysis? Do you remember at the first of the semester what I said about dimensional analysis? You need to get it down. So if you haven't yet, let's do it. We're just canceling units until we get the unit we're looking for. And I still come to problems, and say, okay, how do I do this? What do I know? What am I looking for? And then just cancel until they're done. Sometimes you do a step that, okay, I didn't need to do that. So you erase it and you keep going, right? This happens. That's okay. It's just like balancing. That didn't work. You erase and try again, right? That's all we do. I'm not saying it's easy. Do you want another example or do you want to take a break? Okay, let's take a break. 10 minutes. So back at 28. Okay, we'll just do our last example, and then we're done with this first section. Well, that's a good time. Or are we feeling overwhelmed? If we are, we can do some more. Okay? So let's do another example. So I'm still gonna use this same one just to make it easy for us, maybe. Calcium hydroxide goes into H2O plus calcium chloride. There's a 2 right there. Okay. So now we want to know concentration. We want to know the concentration of this. I know we have 750 milliliters of this solution. And we also have the concentration. It's going to be the same concentration, 0.200 molar concentration of calcium hydroxide. And we still have 350 milliliters of this solution. And we're looking for the concentration of our hydrochloric acid solution. Good? Should pull the mole roadmap up? Is that helpful?
Concentration, what are the units for?
There's a lot of different types of concentration. Is that what you're asking? Okay. We're dealing with moles and volume. So it's going to be moles per liter molarity. Capital M refers to molarity, moles over liters. Good? Okay, let me pull this up. I'm going to shrink that down. I'm going to put it right down here. Is that okay? Can you see that here?
It's the same.
It's the same one, yep. Okay, where are we starting this time? We're starting with our base again, so this is our starting point. Where are we ending? Oh, right here. This is where we end. We can't go this way yet because we don't have that stuff yet, right? So we got to go this way. We're going to take our concentration of our known base solution. We're going to multiply it by the volume, and we're going to get moles of our base. We're going to use the mole-to-mole ratio to get moles of our acid. Then we're going to multiply or divide by the volume. Going this way says divide by the volume, right? And then we got our concentration. 1, 2, 3 steps. Good? Okay. All right, so where do I start?
0.2 moles of the 1 liter solution.
Okay. Could I start with this? Or since I've done it 3 times, do I know how many liters that is?
Yeah, 0.35.
0.35 liters. Now, if you don't know that in your head, guys, figure it out, right? No big deal. So yeah, well, let's just start with 0.200. Am I going to change molarity to moles of CaOH2 to 1 liter of solution? I use that. I'm not going to use that again. Now I multiply by my volume. Right here. So multiply by, before I multiply by volume, what should I do? Or I can do it before or after, doesn't matter. Convert it into milliliters, right?
Liters.
So, or we can convert this into milliliters, doesn't matter. If you wanted to step out here and say 350 milliliters, 1,000 milliliters to 1 liter, oh, and that gives us 0.35 liters. That's a way to do this too. Then, okay, come up here, 3.5 liters. Sorry, yes. 0.35 liters. Good? If you guys are dyslexic like I am, then maybe you should reread everything. And okay. All right. So liters goes away. Now I don't know if I'm dyslexic, so I think I'm just rushing. And this is what I
What
do.
we can put on the, is
What? What's that?
What you put on there, the 0.5.
How'd I get this? Is that what you're asking? Right here. Started with 350 milliliters. I converted it to liters so that it can cancel out with those liters. And according to the map, I start with my concentration and I multiply by my volume. Good? Okay, now, what is it? Now I'm at my moles. I have moles of my base. That's where I am. Now what do? Mole to mole ratio. And it's the same mole to mole ratio. We don't have to memorize it. We don't have to. It's right there. So it's a 1 in front of that. So 1 mole of calcium hydroxide to how many moles of HCl?
2.
Good. Moles of our base goes away. Now we're here. And now what do? Divide by the volume. So I can do the same thing. Let's change that milliliters to what? Why do I need to? Because I'm looking for molarity, which is moles over liter. I have to have liters. So I can come over here, 750 milliliters, do the exact same thing. And I get 0.75 liters. So I'm going to put that on bottom so they can't, I don't want it to cancel out, do I? I just want moles over, so what goes on top? A 1. Because I'm just dividing, right? I can find an answer here if I want and then just divide. That's okay. It's all the same mathematically. Which way should you do it? The way that clicks. If nothing clicks, maybe you're using too much grease. No, I'm just kidding. Just kidding, sorry. So we have moles per liter, and that gives us 0.187 molar concentration of HCl. And I just wrote that on bottom because I ran out of room. It's not divided by, right? Okay.
Isn't that 0.01?
Maybe. It's possible that I goofed. I didn't? Okay. Are we good here, guys? How are we feeling? Feeling like we can do this?
6 out of 10.
6 out of 10? All right, so what does that tell us? We're over 50%, we just need to practice, right? If we're under 50%, then maybe we need something else. And I know you don't have a little thing that says what you are, but
0.200 is 1 mole of. So we put down this here.
yeah, so this is what was given. Was given our concentration and our volume. Molarity times volume gives us what? Do you remember? Do you remember this equation, guys? We're not using this equation, but this is saying the number of moles is equal to the number of moles, right? So MV is the number of moles. You can think of it as a formula, or you can just make sure your units cancel out and you don't have to worry about a formula, right? That's the way I like to do it because my brain's too small to fit all that stuff into, right? Once you use a ton, then you can probably fit it, but yeah.
So you have the 2 mole HCl over 1 mole CaO2 times 1 over.
0.75 liters.
But the 2 mole, the mole right there doesn't cancel because it's molarity, so it would be mole over.
This cancels,
The 1 doesn't cancel, right?
this one does not cancel, that's right. And this one does not cancel. And that's good because we're looking for moles over liters.
So the one
Yeah, this is 1 mole.
No, the other one
No, the other
over
one.
the.
Oh, this is just a 1. Why? Let's do it a little bit different way.
Yeah, wait, why is that?
Let's do it a different way. Okay, let's find an answer here. Let's find our answer to find out how many moles of HCl we get. So 0.2 multiply 0.35 multiply 2. Is it 1.4 or 0.14? 0.14. 0.14 moles of HCl. And what am I looking for? Molarity, or moles per liter. I know we just calculated 0.75 liters, right? So just divide by 0.75 liters now. And the math is exactly the same, but if that helps better, then break it up, do it. And we're still going to get 0.187 molar concentration of HCl. Thanks for asking. Anything else? Yeah, Emma.
Can we do number 3 on section 3?
Yes, we can. Okay, so 0.75 liters, I'm just going to write out what I know. 0.75 liters of NaOH. At what concentration? We want to know the concentration of NaOH. Does that make sense? We'll react with 59 milligrams of HBr. Oh, what are we missing? A balanced equation. Oh. Do we know what the reactants are here? It tells us NaOH reacts with HBr. Does that make sense? So I'm going to write that out. NaOH plus HBr. Oh, dang it. Doesn't tell me my products. What's my products? What kind of reaction is this? Acid base. Specifically, it's a double replacement reaction. They're going to swap partners. This sodium is going to come over with the bromine, and this hydrogen is going to come over with the OH and make water plus NABR. Is it balanced? Yay! It's balanced. It's a 1-to-1 ratio. That's going to make it, well, it's the same, really, if you use dimensional analysis, right? Okay. Now, let's see. What are we looking? We're looking for the concentration of this, right? We're looking for our base, so that means we start with our acid. Okay? We start here. 59 milligrams of HBr. What can we do before we can use the mole roadmap? Convert it into grams. So, should we pull out our mole roadmap?
Yeah.
Just to see what's going on here? Okay, where are we starting? Grams of our acid. That makes sense? Or milligrams, really, but mass of our acid. Then we got to use the molar mass to get to moles of our acid. Oh, hold on, where are we going?
The grams of.
In the end, what are we trying to find? Oh, right here. So the only way to get there, the quickest way to get there is this way, then here, right? Does that make sense? Okay. So again, if you guys like this mole roadmap, write it on your little reference card. Or take a little snippet and print it out and paste it on, right? Whatever you got to do.
Isn't this on the little paper they give us?
this part is.
No, I saw the other stuff on there.
You did?
Yeah, it's not next to it like that, but it's like, it's on there.
Oh, is it?
Yeah.
My last one was different. I don't know if they're like in the process of converting or changing, but I would just write it down in case. Cause I think
Huh.
the last time I took the test, it
Because I submitted this one to put in, and now my students are saying, no, that's not the one I got.
I remember seeing all the like logs and stuff on
Yeah, that's on there.
Yeah,
But the mole roadmap, is it only this part?
I think so.
It's the whole
other
thing?
part is just
I'm not
underneath
sure if
it.
it has everything.
Okay. If it's there, great. But according to what I saw, it says, so I submitted one file. And it had the periodic on one side and this thing on the other side. And then I went and looked at my queue or my test score, and it says 2 files. And I clicked them, and one of them was the old version of this, so it didn't have this part right here, and the regular periodic table on the other side.
Maybe I have a different one, so I'm in like a different class.
It should be all the same. If they changed mine, they should have changed everybody's. That's not fair.
It's not fair, you play cards,
Oh.
man.
And maybe that's why they're doing it. They get cards. Whatever. They're not gonna. Maybe that's what happens. I don't know. So, if you want to chance it and say, I think it's there, okay. But maybe I don't know. Your call.
Just write it down, guys, don't be rude.
Because this and the rest of the stuff is really the only, it's on the reference sheet. Really the main stuff you need for this exam. So I would definitely, and of course you need no polyatomic ions, but, so, you should get those down. Whatever, I'm almost done. Okay. If you're gonna take the final, you still have to know it, okay? All right. Oh, I erased everything. So I'm starting here and I'm ending here. So that's my path. Are we good? All right. So I changed milligrams into grams. Well, I have to have grams to start this map, right? So 1,000 milligrams to 1 gram. Milligrams goes away. And of course, this is HBr. And now what do? Molar mass of HBr.
80.908.
What is it?
80.908.
80.908, or just 91 grams of HBr on bottom so that it cancels to 1 mole of HBr. That goes away. So now I'm here, and now I use my mole to mole ratio, which is 1 to 1. 1 mole of HBr on bottom, so it cancels. 1 mole of, we're looking for NaOH on top. Okay, so now I'm here, and now I just have to divide by the volume. And again, if it makes most sense to find an answer there, do it. Find an answer, then divide your answer by your volume, make sure it's measured in liters. Okay, so we can come down here. We already have liters, right? 0.75 liters. And again, it's okay. You don't really have to put anything on top. Do you understand why a 1's okay? Okay. And so now we have moles over liters, and that's what I'm looking for, molarity of NaOH. And do we get something? Let's see, I do have this. Should get 0.00972. Or 9.72 times 10 to the negative 3? 4? you sure?
I did 4, yeah. Well, I used one of these 80.908 instead of 501, maybe that's the.
No, that wouldn't do it.
I used 4.
Then maybe that's wrong too. Maybe my answer key is off.
So when you bring 59 divided by over.
There is one more zero? Okay. So my answer key is a little bit off. Sorry. And that's molar concentration of NaOH. What's your question, Amon?
59 divided by 0.7.
59 divided by 1,000 divided by 80.9 divided by 0.75. Divide all of the things that are on bottom. And everything on top is a 1, so we don't have to worry about that.
0.72 times 0 to negative 9.
What's that?
Which one is right answer?
They're both the same thing. This one's in scientific notation, right? So just depending on how you have your calculator set. You guys know how to change your calculator to be scientific notation or regular notation? If you don't and you'd like to know how to do that before our last exam, then I can show you. How are we feeling? All right. Do you want to try one from section 3 on your own? Maybe some of you already did. How are we feeling? Who's ready to move on? Who wants to practice? Okay. Go ahead and practice one more. Again, you need to do this on your own so that you can do it on your own on the exam. Yes.
It's also the one that.
So it's not a. Oh, are they the same ones as the one above?
Yeah.
Oh, that's nice, right? Yeah, otherwise that would have been hard to predict, right? A little bit harder. Kind of ish. Did everybody notice that? So in section 2 it has 1, 2, and 3. Section 3 has 1, 2, and 3. They're the same reactions. So balance it on the top, and you got it. You got this, Amon?
I look here to put this, what you did here.
So this one right here is this equation right here. There's the reaction.
almost, you will react. If you have 500 milliliters, this much, this one, how it reacts.
So it reacts like this. These two. So, do you have the small roadmap?
Yes, I would like to watch the video thing. There's something. What you did?
So, do we want liters in our answer?
Milliliter, no.
Do we want liters in our answer?
We just do the old fashioned.
We want grams only. Let's get rid of milliliters.
So 1 milliliter is 1,000.
1 liter is the same as 1,000 milliliters. We do that because this, we only do that because this is a milliliter. Now, do we want milliliters in our answer? No. This is the same stuff, right? So we don't want.
1 in each 3.
So 580 milliliters on top. Why does that go on top?
Cancel.
Cancel with those.
What goes exactly?
What goes on bottom? Oh, 1.
1 milliliter.
Just one.
Now,
So milliliters goes away. Now we have moles of NH3. Well, we want this. So how do we go from one substance to a different substance? Mole to mole ratio. Is this equation balanced? You better balance it first.
this is not advanced.
Is it? You check. Is it balanced? Maybe it is, but you need to check. But there's 3 here,
Yes,
there's
it's balanced.
6, we got 2, plus 4, okay, that one's balanced. One of those, and 1 peel for everything, yeah, it looks like it's balanced. Okay, so just make sure. So what do you ask?
Work demonstrations, work and some other assignments. I know you can watch the videos.
Are you gonna take exam 4 today?
No.
When are you taking?
Station.
When are you taking exam 4? But just so you know, Omar, you've been taking it lately, just so you know, the exam 5 and then the final are on the same week.
Yes. No, this example. Next week I take off 2 days to spend this.
Uh-oh.
Here, yesterday, I went to the subsidy. I will make
Okay, I'm gonna get started again.
Because that's, because we can't work with big apps. We have to split up into this like action. So that's what so we can do this, and we can figure out how to mold eventually. Where we have the road that we want to get to mold. So let's do that. Let's try to figure
All right, you guys ready to get, any questions so far?
So if you want, we can just do this section.
Okay, let's talk about pH if we don't have any questions. If we do have questions, please let me know. All right. So pH, anybody know what pH stands for? We've heard it before, I'm sure, right? Good guess. Power of hydrogen ion concentration.
Wait, that's what pH stands for?
Yes. Because we're dealing with logarithms.
Okay, can you give me an elevator pitch of what a logarithm is?
Yeah, here we go. Well, if we want to graph it, a logarithm, I can't remember if it's like this. It might be like this. I can't remember.
Really exponential, right?
Yeah. So, and you don't have to, all you have to know with logarithms, guys, is the button on your calculator. That's it. Okay? I might show you a little bit of how we get what we got, but you have the equations on your reference sheet, so you should be good there. Okay. So the scale of the pH scale starts at 0 and goes all the way up to 14. Now the pH scale is we converted the exponential to nice, beautiful numbers instead of 10 to the negative 14 and 10 to the negative 0. Right? So it makes it nice. And 7's right smack in the middle. 0 is the acid side. So if we have a pH of 0, this is the strongest acid we could have. Okay? And pH of 14, that's the strongest base we can have. I don't know if that's 100% true, but I believe it is. And I don't think we'll have anything higher or lower. I don't think we ever get to 0 and 14 even. So I think we're good. And 7 is neutral. What substance is neutral? Pure water. Okay? And so if you get something in this region, it's acidic. If you get something in this region, it's basic. Good, or maybe in terms of biology, it's alkaline, right? All right. So here is the formula for pH. And you don't have to memorize this, but you have to know how to use it. So the pH, and this is if we don't have a pH strip, right? Or a pH meter. We can test that, okay? But the pH is equal to negative log of our hydrogen ion concentration. Do you remember in brackets means concentration? So this is hydrogen ion concentration. And then, well, we're talking about bases. And if you look at the mole roadmap, we have POH on there. What does POH stand? What does POH mean? Power of the hydrogen ion concentration. Not the hydrogen. Hydroxide ion concentration. Yeah. So we got POH. It's basically the same equation, just dealing with hydroxide ion concentration. We good? Now the tricky part is, how do we find that guy, right? If we know the hydrogen ion concentration or the hydroxide ion concentration, we just plug it in our calculator. Do you guys know how to use the log in our calculator? And in our calculator, it's base 10, and that's all we're going to use in this class is base 10. That's what this scale is based off of, is base 10. So we just get to use that button. That's nice. Okay. Any questions on these so far? Before I do an example? All right. So let's do an example. What is the pH of a solution? We're going to start simple, and then, because in general you won't ever have a question like the one I'm giving you right now, but we'll just start simple. Well, what is the pH of a solution that contains 0.0150 molar concentration of H plus. So make sure you, and we're doing this simple one, to make sure you can use your calculator correctly. So everybody pull your calculator out, and hopefully you have a non-phone calculator so that you can practice this. So we're going to just, our pH is equal to negative log of our hydrogen ion concentration, which is 0.015. So you push your negative symbol, not your minus button, then log, then 0.015. And depending on your calculator, you might have to put in 0.015 log and then negative. I don't know if anybody has that kind of calculator in here, but if you do, just make sure you know how to use your calculator. Okay?
Sorry, do you know if LN log is the same as log?
It's not.
No, that's natural log.
Has to be LOG.
I had to press mine twice. It went from LN to
Oh,
log.
weird.
And that's why we're doing this simple one, to make sure we can type it in our calculator. And we get 1.824 rounded to 3 decimal places. What are the units? No units. Woo-hoo, we like that. Okay. No units. Well, we don't have to write any units. We'll leave it at that. So does that tell us this is acidic or basic? Acidic. It's closer to the 0 side, right? So, yeah, question?
Yawning.
Okay, don't do that. I'm just teasing. Just kidding. All right, so oftentimes we're not given the H plus concentration. We have to calculate it. And I'm going to show you over this, I don't know if we'll finish today, but the next while I'll show you how to calculate the concentration of H plus. Okay? So let's do another example. And this is going to kind of combine what we just did into the pH. So stoichiometry or dimensional analysis. All right, so let's say we have, what is the pH of a solution that has 0.0125 molar concentration of HCl? Okay. We're looking for pH, and so we write down our equation. pH is equal to negative log of the hydrogen ion concentration. Therefore, this tells us we need to know what the hydrogen ion concentration is, right? So how do we find the hydrogen ion concentration if we're given molarity of an acid? Now, we can do this the long way, and I'll show you the long way just to help you to understand why we can do what we do. So HCl breaks down into H plus, because if this is aqueous, right, this dissociates into H plus and Cl minus. Well, what's the mole-to-mole ratio for HCl to H? Oh, 1-to-1 ratio. Can anybody tell me the concentration of H plus? Right there. It's a 1-to-1 ratio. And let me prove it to you. We got 0.0125, and I'm going to change molarity to moles of HCl per 1 liter of solution. Okay? If I'm dealing with hydrogen, this is all the same solution, right? The volume's not going to change. You with me? So now, I'm going to go, okay, I want moles of H plus. So for every 1 mole of HCl, I have 1 mole of H plus. But do you see how if you can see that it's a 1-to-1 ratio just by looking at that, you don't even have to do this, and you don't even have to do this. But if it doesn't make sense in your brain, then do this. You with me? So if we do that, we're going to get 0.0125 molar concentration of H plus, because we still have moles per liter. Does that make sense to everybody?
So there's still 0.0125 moles of hydrogen in HCl because
So,
HCl has
It's a 1-to-1 ratio. Yep. So then we just plug it in our calculator. pH is equal to negative log of 0.0125. And we should get 1.90-ish.
What is the log? Is it a kind of number?
Log is that button right there in your calculator.
Yes, log.
That's it.
Is it a kind of number to?
It's just an exponential form. I'm not gonna bore you with how to use logarithmic math, but we're just gonna use the button. Sounds good? I mean, it's not boring, but most people, okay.
It is boring.
I got 190.
All right, are we good? All right.
That's
So before we do any harder ones, when do we use POH? When we have a base with hydroxide in it, right? Okay. So sometimes we start with the base, and we got to find the pH of our solution. It's like, hold on a second. Does a base have a pH? Yeah, it's going to be up in the closer to the 14, right? So we still have to find the pH because has anybody ever seen some POH strips? No, we don't have a device that measures this. So basically this is just a way to convert to pH, right? And I'll show you how we use this on the mole roadmap in just a minute, okay? All right, so let's do, let's give you an equation here. pH plus POH is equal to 14. We add these values together, we're gonna get 14.
Every time.
Every time. And we can solve for pH by subtracting POH to both sides, and we get 14 minus POH. Does that make sense in your mind? Or if we're starting at an acid and we want to go to base or whatever, right? POH is equal to what? 14 minus the pH. Sometimes we do that if we want to find the concentration of our base, right? So this equation is also on our reference sheet. It might be this one actually.
It's the,
Yeah, it's this one right here. Okay?
Bases, will hydroxides always be base,
Strong base.
strong base? Okay.
And a lot of times when we're dealing in the real world, yeah, we deal with strong bases. But we also, especially in your field, we deal with buffer solutions. We'll get to that, which is weak acids and weak bases. But if we want to change the pH, we either use a strong acid or a strong base to do that. Okay? So we'll get there. Any questions with that formula? And again, that's given to you. You just have to know how to use it. So let's do another example. What is the pH of a 0.0105 molar concentration of magnesium hydroxide?
More,
Yep, molar concentration, molarity. Remember, this means moles over liters. Okay. So, yeah, where should we pull out the mole roadmap to kind of see how we do this? You guys liking this map yet? Okay. All right, where are we starting here? What do we know? Concentration of our base. We know that. And what are we looking for? pH. Up there it is. So we do log of OH concentration. That means we have to know the OH concentration, right? So first step, determine what the OH concentration is. You following?
1 minus,
And then, once we have the pOH, then we do 14 minus the pOH to get pH. 2 steps. Well, 3, because we have to find the OH, right? Can anybody tell me the OH concentration? If you can't, no big deal.
Is it,
You said OH?
The OH concentration.
Is it 1.979?
It's not. That's okay, we'll get there. Is it a 1-to-1 ratio?
Wait, then is it 0.00?
How many of these do we have for one of those?
2?
A 1-to-2 ratio. So, to do this using dimensional analysis, we're going to start with 0.0105, and I'm going to change it to moles of magnesium hydroxide over 1 liter of solution. And for every one of those, 1 mole of MgOH2. How many hydroxides do we have? 2 of them. Does anybody need a chemical equation to do this? If you do, I'll show you. Okay. 2 moles of OH minus. Magnesium hydroxide go away. Now we have moles over liter, our concentration of our OH. So that's equal to 0.021 molar concentration of OH minus. Are you with me? So all we do is just multiply by 2, right? Sometimes we divide by 2, so don't just say, oh, if it's a 1-to-2 ratio, just multiply. No. You got to use dimensional analysis to make sure you're doing it correctly. Good? Always good idea to just write everything out. Okay. All right, so now I know my concentration of my OH. Now I can do log, negative log of OH minus, and that's going to give me my pOH. So we do negative log of 0.021, and that's going to equal what? Well, 1.68. You with me? Any questions so far? Now, we need to find pH, so we got to do 14 minus the pOH. So it's 14 minus 1.68, and that's going to be 12.32. How you feeling with that? And this mole roadmap tells you exactly what you got to do, other than it doesn't tell you how to get to the OH. That's just the mole-to-mole ratio, you got to get there. Same thing with the H+. Same thing with the liters to milliliters. It doesn't give you the basic conversions, it gives you the main conversion. Good?
Is this like power of hydrogen that we're measuring, like more or less how freely it wants to give away its hydrogen? More or less? More or less?
Or take in a hydrogen ion,
Right,
right?
yeah.
Yeah. It's just an exponential scale.
I don't like it.
You like it?
I just can't like visualize it super well, so it's tough for me to like wrap my brain around.
Have AI help you there.
That's a good idea.
All right. Let's practice this a little bit. Practice section 4. Do some of those right now. Do you want to try any more of those together? Yeah, Andrew.
Yes, so like the second one down,
On the left side?
yeah. Well, I guess all I need to know is whether that's pH or pOH.
Great question. We have to know if it's an acid or a base. Does it have an OH in it or does it have an H in it?
It has an H,
Is that an acid or is it a base?
acid.
Then
Okay.
we don't have to convert it from
Because
PO.
the
Yeah.
CLO is its own entity, right? Like there's, like the O and the H aren't gonna interact.
Yeah.
right?
Well, that.
Okay.
How do we know? Because that's a polyatomic ion.
Yeah, okay.
So that's not going to split apart. That's a. Remember, polyatomic ions are covalent compounds. Yep. It's not going to dissociate. Any other questions on section 4?
How do you do the 2 milligram of
2.3 grams? All right, yeah, let's do the very last one. 2.3 grams of calcium hydroxide in 1.85 liters of solution. So we just want to find the pH. What do we have to find first? If we don't know, let's go to our mole roadmap. What are we looking for on our mole roadmap? We're looking for pH. What are we given on our mole roadmap? Grams of base, right? We're here. Go to grams to moles. Then we're going to divide by the liters to get molarity. Then we're going to use negative log of OH once we find the mole to mole ratio of calcium hydroxide to hydroxide, right? Then we find the POH, or 14 minus the POH. That's it. 1, 2, 3, 4, 5 steps, right? But they're not hard steps. So if you want to just do one at a time, 2.3 grams of calcium hydroxide. We're going to convert that into moles. We have to go to moles for going to anything, right? So this is 40.08, is it? Plus 2 16s, 2 oxygens, plus 2.016 for the hydrogens. And we get 74.096 grams of calcium hydroxide to 1 mole of calcium hydroxide. So grams goes away, good. Now we're here, and we just divide by, we can get an answer if you want. You guys want an answer? Get an answer first? Let's do it. So we do 2.3 divided by 74.096, and we get 0.031 moles of calcium hydroxide. Then if we divide by 1.85 liters of our calcium hydroxide solution, that's going to give us the concentration. And we get 0.0168 moles of calcium hydroxide per 1 liter of solution. And we're looking for pH, so we're here now. Now we got to go to here. What's the mole to mole ratio? Calcium hydroxide to hydroxide. 2-to-1 ratio. So 1 for every 1 mole of calcium hydroxide. Y'all following me? We have 2 moles of hydroxide. So moles goes away. We're left with moles per liter of hydroxide. So we can find an answer here so we can plug it in our POH equation. 0.0168 times 2, 0.0336. And just notice, I rounded that, right? So when you round it each time, your answer might be just a hair off, just so you know. A hair off's not too bad, right? And that's our concentration of OH minus. Now we're here, now we can do the negative log of OH concentration. So POH equals negative log of this guy here, 0.0336. Log's answer, uh-oh. And that's a 1.47. Should always be getting a positive number for the POH and the pH, right? Always be between 0 and 14, positive. So if you're getting a negative, maybe you didn't do negative log, right? Okay, now we are right here. And now we do 14 minus the POH to get the pH. Therefore, it's equal to 14 minus 1.47, and that's going to give us, what is it?
12.53.
12.53. And let's make sense of that. A pH of a strong base should be close to 14, right? Closer to 14. Make sense to everybody?
Minus 14 minus pH equal to pH.
Yeah. 14 minus POH is equal to pH. We just found the POH. 14 minus 1.47. Good?
So what happens?
Oh, we're overtime, aren't we? Okay, I guess that's as far as we're getting today. What's your question?
So what happens if I mix tomato juice and bleach?
Don't drink it.
I'm gonna make a new sauce for dinner, man.
That's a great question. I've never tried it.
I'll let you know.
Just don't mix bleach and ammonia. It puts off a bad gas that I think is poisonous. Now, people say that, but maybe it's just because you're breathing that instead of oxygen. I don't know. Don't try it. Thank you. Take care. Have a great break, guys. Take care. Don't come on Thursday, right? What? No school on Thursday. It's a Utah holiday.
I have a question.
Yeah.